Hello everyone. In this video, we are going to derive the shape functions of a four-noded quadrilateral element. Before I get straight into the business of deriving the shape functions of a four-noded quadrilateral element, I would like to tell you that this video is particularly for people who are preparing for their examination and who want to quickly understand how to derive the shape functions for a four-noded quadrilateral element, iso-parametric element. So if you want to understand the concepts, maybe I can do a separate video. So this video is not to get across the concept explicitly, but definitely I will be doing the step-by-step procedure to derive the shape functions for a four-noded quadrilateral element, iso-parametric element. So to begin with, let me draw a quadrilateral, which is the actual element. Okay, so let me mark the nodal points. The nodal points usually are marked from the bottom left position, and you go in the anti-clockwise direction. So this is going to be our nodal point number 1. This is going to be our nodal point number 2. This is nodal point number 3. And this is nodal point number 4. Let me entail a set of coordinate axes. This is going to be our y-axis. This is going to be our x-axis. So this is x and this is y. Let me also mark the nodal point coordinates. So this will be our x1, y1. This coordinate at nodal point number 2, it will be x2, y2. The coordinate at the nodal point number 3, it is x3, y3. And at nodal point number 4, it will be x4, y4. Okay, now let me draw the master element. Sometimes it is also called as the reference element. Very quickly, I'm going to draw a square to represent the master element. You can also call this as a reference element. Let me entail a set of coordinate axes. This will be the local coordinate axis. We call this as epsilon. You can call this as eta. Some textbooks use the notation R and S. You can call it as epsilon and eta. All right. So let me mark the nodal points. The nodal points are from the bottom left position. This is nodal point number 1. This is going to be nodal point number 2. This is nodal point number 3. And this is going to be nodal point number 4. Let me mark the coordinates. This will be -1, -1. It's a judicious choice of coordinate. This is going to be 1, -1. This is going to be 1, 1, and this is going to be -1, 1. Okay. All right then. So we are going to derive the shape functions. So the first step to derive the shape function is to assume a trial solution. So step number 1, we are going to assume a trial solution. So I'll write the first step. It is you assume a trial solution. Okay. So what is the trial solution that we are going to assume? We are going to assume a trial solution for the displacement, which is u. It is a function of x, y. Note that the displacement is also a function of epsilon and eta. The reason why I'm saying that the displacement is also a function of epsilon and eta is because x is going to be a function of epsilon and eta, and similarly y is going to be a function of epsilon and eta. Therefore, the displacement u is going to be a function of epsilon and eta. Okay, so I don't want to confuse you, but the trial solution that you are going to assume is a0 plus a1 epsilon plus a2 eta plus a3 epsilon eta. You can call this as your star equation. Right then. So this is our first step. I think our first step, assume a trial solution, that is over. Second step is to apply the boundary conditions. So step number 2 is to apply the boundary conditions. So what are the boundary conditions that you are going to apply? The first boundary condition is at -1 comma -1, at x1 comma y1, the displacement, let me change the color, the displacement at nodal point 1, it is going to be u1. The displacement of nodal point 1 along the vertical direction, it is going to be v1. Similarly, the displacement of the nodal point 2 along the x direction, it's going to be u2. The displacement of nodal point 2 along the y direction, it's going to be v2. The displacement of nodal point 3, similarly, it is u3. It's going to be v3. The displacement of nodal point 4 along the x direction, it's going to be u4. The displacement of nodal point 4 along the y direction, it is v4. Okay. The actual nodal points, they actually get displaced along the plane xy, but the displacement on the plane xy can be resolved, right? Along the x component, along the y component. You can just resolve the displacements. In exactly the same manner, the displacement of the nodal point 1 in the master element, it's going to be u1. And here it is the same value, it's going to be v1. The displacement of nodal point 2 in the master element, it is going to be u2. Here it's going to be v2. Here it is u3. It is v3. It is u4. I'm sorry. And the displacement along the vertical direction, it is v4. Okay. So this is important. You have to mark the nodal displacements, because in the next step you will be applying the boundary conditions, right? So you have to apply the boundary conditions. Before you apply the boundary conditions, please mark the nodal displacements. All right then. So now let me apply the boundary conditions. So the first boundary condition is at the nodal point 1. So I can write at node 1, the value of u is u1. So you can just apply this boundary condition on the trial solution. So the trial solution is saying a0 plus a1 epsilon, and at the nodal point 1, the value of epsilon is -1, so that becomes minus a1. And also the value of eta becomes -1, so it is minus a2. And the value of epsilon and eta, both are -1, that leads to plus a3. I can call this as equation number 1. Okay. So let me apply the second boundary condition. At nodal point number 2, the value of u is u2. So the trial solution is saying a0 plus a1 epsilon. The value of epsilon is 1. And the eta is -1, so that becomes minus a2. And the epsilon is 1, eta is -1, so that is minus a3. Okay. If you just apply the second boundary condition on the star equation that you see here, you get this equation. You can call this as equation number 2. Okay. Let me apply the third boundary condition. You know where the story is heading. If you apply the third boundary condition at nodal point Number 3, the value of u is u3. It is a0 plus a1 plus a2 plus a3. So this is going to be our third equation. At nodal point number 4, the value of u is u4 and it is a0. Let me look at the coordinate. It is a0 and epsilon is -1 and eta is 1. So it is minus a1 minus a2 minus a3. Okay, epsilon is -1 and eta is +1, so it should be plus a2 minus a3. All right then. So this is going to be your equation number 4. Now what you have to do is you just have to solve the 4 equations for 4 unknowns in order to get the values of a0, a1, a2, a3. So once you get the values of a0, a1, a2, a3, you have to substitute those values back in the star equation and in order to get the shape functions. Okay, so now we are going to solve the 4 equations. So what I will do, first let me add equation number 1 and 2. If I add equation number 1 and 2, I get u1 plus u2 is equal to, I get 2a0, a1 goes away, a3 goes away, minus 2a2. Okay. Similarly, I can add equation number 3 and 4. So let me write that. Adding equation number 3 and 4, I get u3 plus u4 is equal to 2a0, a1 goes away, a3 goes away, plus 2a2. Okay. Now I can solve these 2 equations to get the values of a0 and a2. Okay. So maybe I can call this as equation number, I can call this as equation number 5. I can call this as equation number 6. All I have to do is solve 5 and 6 to get the values of a0 and a2. Okay. In exactly the same manner, I'll draw a partition line here. And I'm just going to subtract 1 and 2. Or maybe I can subtract 2 and 1. So 2 and 1 or 1 minus 2, whatever you want to do. So let me do 2 minus 1. If I do 2 minus 1 or 1 minus 2, if it is confusing for you, maybe we can try 1 minus 2. Nothing wrong in it. So we can try 1 minus 2. So 1 minus 2, you get u1 minus u2 is equal to a0 go away. So you get minus 2a1. And if you subtract 1 and 2, a2 goes away, you get plus 2a3. This can be called as equation number 7. And similarly, you just have to subtract equation number 3 and 4. So let me subtract equation number 3 and 4. You get u3 minus u4 is equal to, if you subtract them, you get 2a1 and plus 2a3. Okay, so this is what you will be getting if you subtract equation number 3 and 4. I'll call this as equation number 8. Now, So far, what we have done, we have assumed a trial solution. That is step number 1. You call it as the star equation. Step number 2, you apply the boundary conditions. You can see at x is equal to at epsilon minus 1, eta minus 1, the value of u is u1. Similarly, at nodal point number 2, it is u2. At nodal point number 3, it is u3. At nodal point number 4, it is u4. If you apply these 4 boundary conditions on the star equation, you get 4 equations. Now, we are going to solve the 4 equations. So what I did 1 plus 2, I get equation number 5. I do 3 plus 4, I get equation number 6. I do 1 minus 2, I get equation number 7. I do 3 minus 4, I get equation number 8. Now, all I have to do is solve 5 and 6 to get the value of A0 and A2, and solve 7 and 8 to get the value of A1 and A3. So let me do that. So if you solve 5 and 6, all I have to do is add the 2 so that A2 goes away. You'll be getting U1 plus U2 plus U3 plus U4 is equal to 4A0. You got this by adding 5 and 6. Now, all you have to do is find the value of A0. A0 is equal to 1 by 4 into U1 plus U2 plus U3 plus U4. Great, we got the value of A0. So let me put, okay, fine, good. Now, I'm going to subtract 5 and 6. Let me see what comes if I subtract 5 and 6. I'll be getting U1 plus U2 minus U3 minus U4 is equal to, if I subtract 5 and 6, I get minus 4A2. All I have to do is I have to hit it by minus sign on both sides so that I can solve for A2. So A2 will be equal to minus U1 minus U2 plus U3 plus U4. Of course, 1 by 4 is a common term that can be kept outside. So I got the value of A2. Got it then. In exactly the same manner, I can now solve equation number 7 and 8. So I'm just going to add equation number 7 and 8. So let me see what I get if I add equation number 7 and 8. I get U1 minus U2 plus U3 minus U4 is equal to 4A3. So this gives me the value of A3 as 1 by 4 into U1 minus U2 plus U3 minus U4. All right then. So I can now subtract 7 and 8. So let me see what comes if I subtract equation number 7 and 8. So I get U1 minus U2 minus U3 plus U4. And if I do it on the right side, if I subtract equation number 7 and 8, I get okay, if I subtract equation number 7 and 8 on the right side, I get okay, minus 4A1. That's what I will be getting, minus 4A1. So I can hit it by minus sign on both sides to get the value of A1. So let me do that. Let me hit it by minus sign on both sides to get the value of A1. So A1 is equal to minus U1 plus U2 plus U3 minus U4 divided by 4, or you can say it's 1 divided by 4. So that's the value of A1. So I got the value of A0, A1, A2 and A3. Now all I have to do is take the values of A0, A1, A2, A3 and substitute it in the star equation here. Okay, mathematics is just like moving objects, so remember the star equation. So that is going to be my step number, okay, it's just step number 3 because I have solved all the equations in step number 2 by applying the boundary conditions. So step number 3 is I'm going to substitute the value of A0, A1, A2, A3 in the star equation. So that is step number 3. Substitute the value of A0, A1, A2 and A3 in the star equation. Okay, good. So the star equation is saying u of epsilon comma eta is equal to A0. The value of A0 is 1 by 4 u1 plus u2 plus u3 plus u4. 1 by 4 u1 plus u2 plus u3 plus u4. That is A0 plus A1. So what is the value of A1? So there you go. It is plus 1 by 4 minus u1 plus u2 plus u3 minus u4. A0 plus A1 epsilon plus A2. So what is the value of A2? It's minus u1 minus u2 plus u3 plus u4. A0 plus A1 epsilon plus A2 eta plus A3 epsilon eta. So what is the value of A3? It's u1 minus u2 plus u3 minus u4. Okay. Now I just want to do one more step. I just want to take all the coefficients of take all the coefficients of u1 outside, u2 outside, u3, u4. Okay. So let me bring all the coefficients of u1 outside. So it will be 1. And the coefficient here in this term, it is minus epsilon. And the coefficient in this term, it's minus eta. And the coefficient in this term, okay, I forgot epsilon eta. The coefficient in this term is plus epsilon eta into u1. Let me bring all the coefficients of u2 term. It is plus 1 by 4. It is 1 plus epsilon minus eta minus epsilon eta into u2. And let me bring all the coefficients of u3 term. It's going to be plus 1 by 4 u3 term. It is 1 plus epsilon plus eta, okay, plus epsilon eta into u3. Let me bring the coefficients of u4. The coefficients of u4, it is, for the first term, it is 1. For the second term, it is minus epsilon. For this term, it's going to be plus eta. And for this term, it's going to be minus epsilon eta into u4. Now, in the next step, I'm going to take eta common for these two terms. And again, I'm going to take eta common for these two terms. Let me take eta common from these two terms. Let me take eta common from these two terms. Okay, that's what I'm going to do. So let me do that. The next step, it's going to be 1 by 4 1 minus epsilon. Let me bring that eta common. Minus eta, if I take it outside, I'll be getting 1 minus epsilon. So I can put bracket like this into u1. Similarly, plus 1 by 4, I can write 1 plus epsilon, and if I bring that eta outside, I get 1 plus epsilon into u2, plus 1 by 4 into, I can put a bracket, 1 plus epsilon like this. If I take the eta outside, plus eta into 1 plus epsilon into u3. And for the last term, I can actually put a bracket like this. I can take the eta term outside. It's 1 minus epsilon into u4. Now the last step, u of epsilon comma eta is equal to 1 by 4. I can bring 1 minus epsilon is here. I can take that common outside. I'll be getting 1 minus epsilon into 1 minus eta, okay, into u1. If I take 1 minus epsilon from this term and this term outside, if you take it outside, you get 1 minus epsilon into 1 minus eta, right? Interesting. So next it is 1 by 4. If I take 1 plus epsilon from this term and 1 plus epsilon here, if you take them common outside, you get 1 plus epsilon into 1 minus eta into u2. And in the next step, if you take this 1 plus epsilon common outside, you get 1 by 4 into 1 plus epsilon into 1 plus eta into u3. And here, if you take 1 minus epsilon and 1 minus epsilon outside, you get plus 1 by 4 into 1 minus epsilon into 1 plus eta into u4. And if you look at these terms, this is of the form n1 u1 plus n2 u2 plus n3 u3 plus n4 u4. Okay, so these will be our shape functions. So let me mark that down. So this will be our n1, this is going to be our n2, this will be your n3, and this will be your n4. You can write similarly v of epsilon comma eta will exactly be the same, except for u1, u2, u3, u4. You have to write v1, v2, v3, v4. You will end up with exactly the same equation, which is n1 v1 plus n2 v2 plus n3 v3 plus n4 v4. So this is how you derive the shape functions for a 4-noded isoparametric quadrilateral element. Now, there is another method by which you can actually derive the shape function, which is a shortcut method. Now, how do you derive the shortcut method? That is for the second part of this video. If you look at these shape functions can readily be squeezed out from the equations of the lines that describe the master element. Okay, so that's a shortcut trick. So for now, this is how you derive the shape functions for a 4-noded quadrilateral element conventionally. So you can use this trick in your examination. But of course, there are shortcut tricks that are available. That will be for video number 2. So thank you all for your patience. I really appreciate your time.